Hey everyone, and welcome. You ever look up and see a 400-ton airplane just cruising miles up in the sky and wonder, how does it stay so perfectly level? Well, today we're going to dig into the invisible physics that make it all work. Let's get into the secret world of aircraft stability. So let's start with a question for you. Think back to the very beginning of aviation. What do you think the single biggest hurdle was? I mean, was it getting enough power? Building wings that were light enough? Yeah, those were massive challenges, absolutely. But believe it or not, they weren't the number one problem. The real roadblock wasn't about pure muscle, just strapping on a bigger engine. Nope. It was something way more delicate. It was a puzzle of balance, of action and reaction. It was about creating a machine that wouldn't just get off the ground, but could actually be flown. And here you have it, straight from the guys who figured it out. The Wright brothers knew that the real secret sauce wasn't just lift, it was the ability to actually command the aircraft once you were up there. It all came down to control. And really, that shift in thinking is where our whole story begins. The fact that they focused on control, not just on lift and power. That's why they succeeded when so many others failed. Right, so here's the bottom line. Launching a plane into the air is one thing, but stopping it from immediately flipping over and crashing, that's a whole different ballgame. The real challenge was building something that could get hit by a gust of wind or handle a tiny mistake from the pilot and not just fall out of the sky. And that, right there, is the heart of stability. Okay, so to crack this problem of control, engineers came up with the idea of stability. And it really has two different sides to its personality, and they have to work together. Let's break them down. First, you've got static stability. The best way to think about this is to picture a marble at the bottom of a bowl. If you give it a little nudge, what's the first thing it wants to do? It wants to roll right back to the center, right? That initial urge to get back to where it started, that's static stability. A plane with static stability wants to fly straight and level. But wait, that's only part of it. Now we need to talk about dynamic stability. So let's go back to our marble. When you nudge it, it doesn't just snap back to the center. It rolls back and forth, right? It oscillates. Dynamic stability is all about what happens over time. Do those wobbles get smaller and smaller until it settles down? Or do they get bigger and bigger until the marble flies right out of the bowl? And this table just lays it out perfectly. Static is that initial nudge back to the middle. Dynamic is the story of what happens next. For a plane to actually be stable and flyable, you have to have both. It needs to want to return to straight flight, and any wobble it has on the way needs to eventually fade away. So, how do you make sure that wobble actually goes away? Well, engineers have a very specific name for the force that gets that job done. It's called damping. You can think of damping as a kind of aerodynamic friction. It's the force that literally sucks the energy out of those wobbles, making each swing a little bit smaller than the last, until the plane just settles back into smooth, stable flight. And check this out, because this is where it gets really interesting. You've got positive damping, which is what you want. It removes energy, the plane settles down. But then you have negative damping, and that is a pilot's absolute nightmare. It actually adds energy to the wobble, so it gets bigger and bigger until the plane becomes completely uncontrollable. And this is where modern tech really shines. A plane that's naturally unstable, one with negative damping, is basically impossible for a human to fly. It can only stay in the air with the help of a computer. It's called a Stability Augmentation System, or SAS. Think of it like a superhuman co-pilot making thousands of tiny adjustments every second, artificially creating that damping to keep the plane flying straight. So how do you bake all this into the actual design of an airplane? Well, when it comes to stability, especially with the nose pitching up and down, engineers live by two golden rules. Let's make these super simple. Rule number one, the plane has to correct itself automatically. If a gust of wind shoves the nose up, some force has to exist that automatically pushes it back down. And rule number two, the plane has to be stable at an angle that's actually useful, an angle where the wings are creating lift. I mean, a super stable plane that only wants to dive into the ground isn't much of an airplane, is it? And here's what rule number one looks like when engineers write it down. Now, don't get hung up on all the symbols. All this equation is really saying is that the pitching moment, the thing that pushes the nose up or down, has to have a negative slope. In plain English, if the nose goes up, the force has to be negative, pushing it back down. That's it. And here's the math for rule number two. This little formula just makes sure that when the plane is perfectly balanced, when there are zero pitching forces, it's doing so at a positive angle of attack. Just like the caption says, this is what lets the wings actually generate the lift needed to, fly.
Okay, so we've got the rules, but what part of the airplane is actually doing the work here? What's making all this happen? The answer is probably not what you think.
Yeah, get ready for a bit of a plot twist. You'd assume that the huge main wings are what keep the plane stable, right? Well, for most planes, it's the exact opposite. The way the air flows over the wing actually creates a force that wants to make the plane tumble. The wing is trying to destabilize the whole thing. Which of course brings up a pretty big question. If the wing, the main character of the airplane, is actually the villain of our stability story, who's the hero? What part is fighting against the wing to keep the plane balanced? The hero is a much smaller horizontal surface. As you can see here, it could be a canard up in front of the wing, or, what's much more common, an aft tail way behind the wing. The important thing is where they sit in the air that's already been messed up by the main wing. And for most planes, the unsung hero is that aft tail. It sits way back there in what's called the downwash, the air that's been pushed downwards by the main wing. And because it's so far back, it has a ton of leverage. It works constantly to create this counteracting force that overpowers the wing's bad habits and keeps the airplane flying straight. And this isn't just luck. Engineers have this down to a science. They precisely control this balancing act by calculating what's called the horizontal tail volume ratio. It's basically a formula that takes into account the tail size, how far back it is, and the wing's size, and it lets them dial in the exact amount of stability they need for any given aircraft. Which brings us to one last, really fascinating question. We've spent all this time learning how stability is the key to control. So why on earth would the designers of the most advanced fighter jets on the planet tear up the rulebook and build planes that are intentionally unstable? Well, that's a whole other story about trading stability for pure agility, and maybe a topic for another time.